what charge would be stored in 180 microfarad. 10 to the minus 6 is what micro, and so farad is just a shorthand for Faraday, the dude that you saw in the movie who's connected all the dots between these semesters, one of the dudes, when 120 volts is applied to it. So this isn't any sort of rocket surgery. So you'd have 180 times 10 to the minus 6 times 120. You could use the symbols, but as long as you're dealing in farads for capacitance and voltage for voltage, then you can just multiply the numbers, and you'd get 2.16 times 10 to the minus 2 coulombs. And we don't tend to, when we deal with these sorts of things in electricity, and a lot of things in science, but not all of them, we tend to write it in engineering notation. So this would actually be 21.6 times 10 to the minus 3 coulombs, which would be most properly written as 21.6 millicoulombs. So we have some standard conventions for how we express certain kinds of answers. All right. Another simple one here, the same setup. Picofarads, so that would be trillionths of a farad. 5.5 volts, and so we're going to get 4.4 times 10 to the minus 11th coulombs, and it would be best to bump that up, the coefficient, by a factor of 10, which means the multiplier divided by a factor of 10, which means that what I'm dealing with is 44 picocoulombs. And that makes sense. I have a 10 to the 0, if you will, something times that volts, one-digit volts, and pico charge. I'm going to have pico, or pico capacitance rather, pico charge. All right, so simple ones, and in this case we are basically demonstrating the relationship that charge would have to capacitance and voltage. Capacitance in these examples is going to be dependent, directly proportional to the capacitance of whatever that charge is resting on and the voltage applied to that thing. Okay, more voltage would mean more charge, because more voltage means pushing more charge around. More capacitance would mean more charge. And so what is capacitance dependent on? Well, one of the equations, if I remember correctly, is that it is the area per distance, and then the electric permittivity constant is out in front of that. So directly proportional to area, inversely proportional to distance. But there's the geometry of the place is one of the limiting factors on capacitance, and so is the physical system. And when I say physical system, I mean the voltage that might be, how is the electric field behaving on that geometry of the physical apparatus. And another one here is just another simple version. We have, I didn't give example 9.8, so we'll just skip that so you can scribble that one out. Nothing new to do in that one anyways, so might as well move on. And again, some simple things here. Calculate the voltage applied here, so that means voltage is going to be charge per unit capacitance. So let's just think about this. Now, it's not just that we're solving for voltage, we can get away with that, but what we're saying is now the voltage that I can apply to something is going to be dependent on the charge that's on that thing and inversely proportional to the capacitance. Let's think back to what we were messing around with in the simulation. If I apply a voltage to a capacitor, it'll get so much charge on it. If I disconnect that capacitor from the voltage source, the charge that's on it is stuck there. So now, if I change that system with a fixed amount of charge, then if things change, it's because other things that were free to change changed, which I can. I can change the separation distance, and I can change, well, you normally can't change the area of an object, right? So the only thing that we could change here, we could change capacitance in this little thought experiment we're doing, modifying this problem, if we change the separation distance. Okay, so this equation makes sense in a particular context, one where I can change the capacitance. All right, so the charge was 3.1 times 10 to the minus 6 over 2 times 10 to the minus 6. And so we just get 1.55 volts out of that. So as long as things are in coulombs, all right, and I'm sorry, capacitance isn't coulombs, capacitance is farads. So now it appears that voltage, in addition to being, it's work done per unit charge, so we could maybe think about what those units would be, but it's coulombs per farad is a way to think about volts, how many charges per capacitance, if you will. And then this last one, what would the voltage be? Again, Q over C. So we'd have 0.16 times 10 to the minus 3 over 8 times 10 to the minus 9. And that should give us 2 times 10 to the 4th volts, and that would just be 20 kilovolts. Or 20 times 10 to the 3 volts. So simple calculations, nothing outrageous, but lets us put some legs on the, I gotta change pages here. All right. This new problem, find the capacitance of a parallel plate having plates of area 5 square meters. That's a really big capacitor, even if I rolled it up on itself. So usually capacitors are little can things, as big as the tip of your pinky. But that was a larger rectangular plate, like a ruler sized thing that got rolled up on itself. So, but a 5 meter square area, that would have to be a really thin capacitor plate if we were going to roll it up into a small size. But again, don't care that much. Just we could pick any area that we wanted. All right. So find the capacitance. Well, there's this kappa symbol, and Teflon has a dielectric constant. So this thing lets me point to this thing about the dielectric. So like we saw in the video, if I put certain kinds of material between parallel plates, basically I increase capacitance because all we're doing is putting a particular kind of material that won't allow charge to transfer, but it will polarize. Just like if you go all the way back to when we first started, where we had those thought experiments with, if I have this charged sphere come near this other one, what happens to the charge distribution? It's the same idea. If I build up charge on one plate right next to this dielectric between the other plate, if those molecules have charges that are polarizable, that's a word, then everything will turn and increase the strength of the field in that location. So this dielectric constant, every material that we use as a dielectric, we've computed the dielectric constant. So it's just a number. In this case, it's 2.1. You could look that up. You know, if you Googled what's the dielectric for Teflon, it would tell you it's 2.1 because Google knows everything. Google is our friend. All right. Epsilon naught, we use this every now and then. It's just a constant. Its numeric value is 8.85 times 10 to the minus 12. Happens to be farads per meter. Okay. But that's not nearly as important. The area was 5 square meters. And separation distance is 0.1 millimeter. So that would be 0.1, but we need it to be in meters. So we would have to convert it. All right, so just to be clear, 0.1 millimeters would be this many meters. I didn't use units in the rest of it, but then we just compute all that stuff, and we would get 0.93 times 10 to the minus 6 farads, or just 0.9. Having troubles writing my 0.93 microfarad. That's the capacitance of this particular capacitor with a particular kind of dielectric. Notice that none of the inputs to this were anything but constants and geometry. So what's the capacitance of this particular capacitor? Meaning, based on its physical properties, it has this capacitance of 0.93 microfarads. But as we've seen, depending on how I configure this thing in a system determines how much charge, voltage, energy, etc. Those all things will be variable according to that. But generally speaking, at this point, once you build something like this, these are not going to change. You know, you buy something, you stick it in the circuit, it's not like its area and separation distance change. I'm not even aware of a capacitor that's in an actual useful device that you could change area and distance on. If there is one, it's in somebody's physics lab somewhere, and they've custom built it because at universities you have budget for that sort of thing. Community colleges, we don't have that kind of money, unfortunately. So, any questions so far? Just want to kind of connect some dots, and computations do give us a little bit of ability to see how things are connected. They have their strengths and weaknesses, and doing the lab has its strengths and weaknesses as well. All right. What is the capacitance of a parallel plate capacitor having plates of this area separated by that distance, and they have rubber for the dielectric in between? And then what charge hold to it? So here I don't give away the equation, but we just used it. The capacitance is going to depend on, and so here's the thing. If there's no dielectric, kappa is 1. That's funny looking K, it's a kappa. But you could always put that kappa in the equation. We tend to not to do it. Try to draw a funny kappa, or funny K. Epsilon naught, area. Making the K as tall as the epsilon sort of indicates that it's not a Coulomb constant. All right. And let's see here. 6.7 is the dielectric constant for rubber, neoprene rubber. We have our electric permittivity constant, which is a measure of the ability of a vacuum to tolerate electric fields, if you will. And so in this case, the dielectric constant changes the electric permittivity of that space. So before we move on, I actually want to, since it's there, these two things together, okay, this is dielectric changing the properties of this space. And so we've said it a few times, but it's one of those ethereal things that most people just like, okay, whatever. Epsilon naught all by itself refers to a vacuum, meaning out there in space between the galaxies. That's where we have our truest vacuum, so to speak, where there's 1 micron size piece of dirt, per square meter, or 10 square meters. There's nothing there than whatever space is. And so now the space between the capacitors, since it's generally not a vacuum, it's usually some sort of dielectric material. It could be air. You could put one in a vacuum tube of some sort. In fact, we do that sort of thing. And in that case, kappa would just be 1, and you have epsilon naught as your thing. And then I think air has its own dielectric. Anyways, so just a little sidebar there. See the problem lets me talk about something important. Let's see. The area was 1.5. And separation distance of 0.02, but it's millimeters, so we've got to bump it up to meters. And you crunch all them there numbers, and you'll get 4.4 microfarads. So we'll have some quiz material that looks like this stuff, where you have to do some plugging and chugging and computating. I know that's a bad word, and there are no English professors in the room that I can irritate. But if you want to tell on me, feel free. Go right to Heather Moulton and tell her that Clark said betterer and computating. And she'll twitch for a minute, laugh, and go, yeah, I'm used to that. I'll get him later. All right. Meanwhile, back at the ranch. Part B of this problem. What charge does it hold when 9 volts is applied to it? Well, we started with that one. Charge is directly dependent on capacitance and voltage. We just computed the capacitance. And the voltage they're asking about is 9 volts. And so we'll get 4 times 10 to the minus 5th coulombs, which that would be, you could say 40 microcoulombs. Because if I bump that 4 up by a power of 10, I have to bump the multiplier down a power of 10, and that would give me a micro, 10 to the minus 6. So that problem kind of lets us go closer to full circle on how a capacitor is used, how it's constructed, and then how it's used. How does the construction of it relate to putting it in a system? All right, so now we're going to switch gears and talk about these things placed in circuits. So you may not have watched the video where I explain this. Had the original lab simulation worked in our computers, we could have actually experienced how placing these things in series and parallel changes things. And so there are capacitor circuits where series and parallel results in one kind of pattern. And there are resistive circuits, things we'll study after spring break, and the pattern is flipped. So when you get one kind of effect with capacitors in series, you get the opposite effect with resistors in series. Same thing for putting these things in parallel, resistors or capacitors. The equations are the same structure, but when capacitors are in series, you add them this way, but resistors add in series the way that capacitors add in parallel, and vice versa. So we'll see this change here. So what these equations that pop out now, we'll see those same things again. I do explain these equations in the video, though, so if where you're at in your note taking on those, but we'll just get through the computations here. So here's a circuit. I could wire things up in this way. I could connect wires to capacitors, and then if I put a voltage across the top and bottom of this, then these capacitors will build up charge in particular ways, and then we would do something with them. And so this is not going to be this isn't a useful circuit. It might be a part of a useful circuit. So we'll get to that later. All right, so in this problem, find the total capacitance of the combination of capacitors in this figure. All right? So what we have here is these capacitors 1 and 2, they are parallel to one another, okay? They are literally, physically parallel. They're running side by side. And a parallel capacitance, that's what I mean by the big C, our symbol for capacitance, sub P, I mean for parallel capacitance. You can add them this way, just literally the sum of the capacitance when they're in parallel is just a simple addition. All right, and so 10 micros plus 2.5 micros, this isn't any rocket surgery, we're going to have 12.5 microfarads. So in the video I talk about this, your book would tell you parallel capacitance is simple addition of the capacitance. We'll find that series capacitance adds in a reciprocal fashion, a 1 over this plus 1 over that equals 1 over the whole. It's just a difference. I believe that is a harmonic mean? I need more coffee. It is a special kind of mean. All right. So we have that part. And so if I'm going to find the total capacitance, I have to somehow put together all the parts. And so parallel parts, you would even expect that a parallel part would add differently than series parts. You wouldn't expect the same pattern in that regard. And that was the intent of the lab that preceded that we weren't able to do, but I'm trying to not be bitter about. All right. So one of the things that we do, though, is we would rewrite this circuit this way. This is an equivalent circuit. Okay? This right here, I could produce the same effect with 2 capacitors in series, as so long as the first capacitor had the same capacitance as what these two in parallel give me. And you're thinking, okay, well then why would you do two things? Well, as we'll find with circuits, having multiple branches within a circuit gives you certain opportunities, advantages. And if you need those advantages, then it pays to have them in parallel. If you don't, then it wouldn't make sense to make a parallel circuit, right? And so more on that later. But anyway, so we could pretend that the parallel network, if you will, this chunk, is behaving like a single capacitor, because that parallel branch, the whole thing, is in series with this third capacitor. So whether it's 2 or 10 capacitors in parallel, if their total capacitance is 12.5, they all would behave the same with respect to what comes after. All right? Well, series capacitance, which I'll designate as C sub S, is written this way. 1 over the total capacitance in series would be 1 over the first one in series plus 1 over the next one in series, and so forth and so on, as many things that you have in series. That would never stop changing. So you have a, and I've put it over here. You can see this is the general formula for series, and this one here is the general formula for parallel. All right. So what this means is now when I solve, I would just have the product over the sum. The last time you saw this would have been in algebra class when you had what they called work problems. If Johnny can paint the garage in 8 hours by himself, and Johnny's dad can paint the garage in 12 hours by himself, then how long would it take them to paint the garage together? So provided that they don't fight, you would expect that it would take less than 8 hours, less than the fastest contributor. Problem is you can't add their total times. You can add the rate at which they work. All right? And so this model of 1 over the whole equals 1 over the sum of 1 over all the parts is a particular kind of work computation, and it is an average. It's a special kind of weird average. It's a weighted average in the most general sense. And as you know, all generalizations are false. Get it? All generalizations are false. Can't remember if I used that one before. All right. So now all I'd have to do is, since I converted a parallel series capacitor circuit into a series capacitor circuit, this is all I need to compute this formula I just built. So if I take C3, which was 0.3 times 10 to the minus 6, times the parallel capacitance, which was 12.5, I'm going to back up here. Since everything is micro, I don't even need to bother with. Oops. And the sum of those two would be 12.8 microfarad. So you're going to get one of the microfarad units dropping out, obviously, meaning that it's all numbers times some number of microfarads. Yay. So all of this crunches down to 0.293 microfarad. And I guess if we wanted, we could have 293 nanofarads, whatever floats your boat. So that's it. So this is a little intro to the circuits side of using capacitors, which is where they're useful. That's our most useful application of these toys, is to put them in a circuit and put them to work doing stuff. All right. Number 9 here. Oh, that stinks. FYI, guys, so Michelle's looking at the screen and it's backwards on the camera. What a useless camera. Why would it do that? There's probably some physics reason for that. I'll think about that later. Oh, man. All right, I'll send you the notes later. Actually, I'm doing multiple videos of this, so you'll be able to watch the video as well. So if you want to duck out, Michelle, if it's making you go crazy, that would be difficult to deal with, watching it written backwards. Cruel and unusual punishment. I'm just trying to imagine why they would configure a camera for this use and have it be that way. Well, I think they're expecting that the screen would share, but for some reason, me putting a different source on this screen only works on these projectors. It doesn't connect electronically into the blackboard, which I find odd because it's on this monitor. It should connect. Oh, well. All right. The number 9. Suppose you want a capacitor bank with a total capacitance of 0.75 and you possess numerous 1.5 microfarad capacitors. What is the smallest number you could hook together to achieve your goal? So we need to figure out what that number would be. So what this is saying is that N C will equal CP, which means that N's going to be this parallel capacitance over the total that I want. And so and you have to do it in parallel, otherwise you'll never get up to. If you have a bunch of things that are smaller, all right, 1.5 micro is smaller than 0.75. So the only way that you can connect them is to connect them in parallel. So if you go back to those equations in the previous problem, you see that you must construct a parallel circuit if you want multiple capacitors to lead to larger resistance. The opposite will be true with resistors. The more resistors you put in parallel, the lower that total resistance goes. So it's using the exact same opposite formula. All right. So we know that we're looking to get all the way up to 0.75 farads by adding things that are much, much smaller. So farads per farads is nothing. It's a count. So you do this math, you get 500 capacitors. That's a lot. So hopefully there's a big box of these capacitors. And that is totally impractical. I can't imagine why anybody would have a 500 capacitor network unless they're so super small it's the only way to cram them in there. Who knows? This is nuts. But the main the utility of the problem is just really conceptual. It's understanding one, what the total capacitance could be understood as a number of capacitors. And then, so that's kind of a no-brainer, because in the number n times capacitance, okay, it has to be this way when they're in parallel. And the reason why is because C1 and C2 are all identical. so we didn't say that, but C1 equals C2 equals C any index you want, all right? And so that's why we would be able to write that in parallel, which is the only way to get a stack of the identical, or to any number of smaller ones to add up to something bigger, is only in parallel. So the usefulness of the problem is in its theoretical import. Otherwise, totally impractical. All right, moving on. So number 10, here I have a parallel network, but inside of the parallel network there is a series part. So I'm not going to rewrite the whole 1 over part, but if you remember, the series equivalent, if I could make a capacitor, a single capacitor that does the same thing as these two in series, I would compute that as the product of those two things over their sum. And we just did this in the last problem, so otherwise this would work out to 1 over the total series equals 1 over the first one plus 1 over the next one. All right, and if we plug and chug all the values in that one, we'll get 0.3 micro times 10 micro over 10.3 micro, and that's going to work out to be 0.291 microfarad. Yay. Then this thing is in parallel with that thing. And so the parallel thing is just a sum. It's going to be the one on the left plus the one on the right. And so 0.291 plus 2.5 is going to give me 2.79 microfarad. Easy peasy. So just to reminder, the series stuff was in blue, parallel stuff in red. So the process of finding total capacitance is fundamentally the same as the process as finding total resistance, something we'll do when we get farther into circuits. But you always are doing this maneuver where you collapse things that are in parallel and or series by means of these equations. And you essentially create an equivalent capacitance. So we could do the same job that this series parallel network of capacitors is doing by simply getting a single 2.79 microfarad capacitor. So I'm going to kind of make up and guess at an application of this in the medical field. I've told you that your nervous system is essentially a bunch of capacitors. And sometimes those are things that are, and some part of the nervous system would be a series set of axons or whatever, muscle actions, whatever, parallel, etc., etc. And so what if I can't fix the inside parts, but maybe I could add something to the parts in a way that changes their capacitance. So just imagine that our systems are as simple as capacitors. Could this drug, this gene therapy, this actual device implanted? So somewhere, somebody doing this kind of biomedical engineering kind of work has to think this way. And so they aren't necessarily a biomedical engineer. In fact, they're more likely to be a biochemist or some other thing, but that could be an engineer. In fact, that's happening. I shouldn't say it's unlikely. But anyways, so somebody has to think this way. And so if you ever get involved in the research level of your craft, then you would eventually come back to this sort of thing, because your body is an electrical system more than its other things. Okay, so voltage, current, all those things show up in the way that our bodies work. There's a reason why, when the defibrillator paddles, they charge them up to some number of, I think it's this many joules. I think I've actually seen that in a real setting. How many joules we're going to crank this puppy up to? How much energy we're going to deliver, because there's a certain amount of charge associated with that energy. All right. Find the ooh, this will be fun. So, what could we do? So it doesn't really matter where you start, but over here in this one branch, really what I need to do is I need to combine those two before I try to collapse the rest of the parallel network. Or if I try to collapse the other parts of the parallel network, I can't do this far right branch area until I collapse this little sub-branch. So one way or another, you'd have to get to this spot. And so here we have a parallel network that's in series with something else. And we know that when they're in parallel, it's just the simple sum of those things. All right. And so this is going to be 15.75. I hope we don't have to actually write out the sum. All right. Then this part in series, so this series thing, we could write the 1 over version, etc. But we know it's going to be a product over sum. It's going to be the product of the one that was all by itself in series with this parallel branch, with this new version, this single reduction of it over the sum of those two things. So here we'll have to write a thing or two, 1.5 times 15.75, and that's going to be over their sum. You crunch all of that, and you get 1.37 microfarads. So interesting, in parallel, they get bigger. In series, they get smaller. The total capacitance. All right. Then, let me kind of redraw here what we went from. So let's see. I'll draw the first reduction in red. The first reduction would have had us C5, C6, C4, C3, and CP. So that first reduction, what I wrote in red symbolically, lets me, I could just replace that red parallel branch on the right with a single value capacitor of 15.75. The blue reduction would have me, I'd still have C5, C4, C6, and now, I need to correct something here. This isn't C3, that's CS in series, forgive me. So CS, so that's what we've been doing to the circuit. So our computations would let us reconfigure a circuit to be simpler. This is almost like in algebra, you know, if you combine like terms and blah, 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 you can simplify the equation. We are simplifying the circuit so that we can do computations on that circuit. We wouldn't actually change the circuit because it was designed to have this many branches for some other set of reasons. But we have to simplify it mathematically in order to start the process, so to speak, of applying voltage and seeing what that will turn out to be. All right. So we have one more reduction to do. We need to convert these puppies into something else, and so they are in series. So it would probably be, and forgive me, I should have labeled that first series thing as probably C123. I'm going to call this C56 because it's going to represent the collapsing of 5 and 6. If you wanted to go back and change this one, that would be totally cool. You could also go back and change CP to C12. That would be a better way to do this because it helps you keep track of what you were collapsing. All right, C56, how's that going to go? It's in series, so it's going to be product over sum. C5, C6 over the sum of those two. And you can plug and chug all that. I'll just give you the number because it's the same old math as before. So now C56 has been simplified, and if I were to draw that circuit, now I have a C56 in parallel with a C4, which is in parallel with a C12. So now I've simplified mathematically and then represented that simplification diagrammatically. So now it's just these things are in parallel, and that's simple. So the C total, if you will, you could call it 1, 2, 3, 4, 5, 6 if you wanted to. I forgot to put my 3 over here. Yep. It's just going to be the sum of all those. So C1, 2, 3 plus C4 plus C5, 6. And if you add up all them numbers that we just did, where did my... 15.75, 1.37. Oh, I'm sorry, the 8. So this adds up to 11.4. Because we are adding an 8 to, let's see, 1, 2, 3 was 1.37, and the 5, 6 was 2.059. So technically, this isn't difficult at all. It's just a little bit tedious. And it's this kind of math shows up in intermediate algebra. It doesn't even show up. It's not like you have to wait till pre-calculus to do this. It was in intermediate algebra. These sorts of that work problem, that paint the house problem, fill the pool problem, that shows up in intermediate algebra, right? So I think what we can do is just sort of